Computers have undoubtedly become an essential part of modern life. But how did we get here? The development of the modern computer is an ongoing process that actually took several centuries. To understand the modern computer, we first have to look at ancient computing devices and algorithms. The first such device is the abacus. Its exact origins are unknown, however it most likely originated from ancient Mesopotamia. The abacus or counting frame is a calculating tool that was first used in the ancient Near East, Europe, China and Russia. This was done centuries before the adoption of the written Arabic numeral system we are used to today. Abacuses were and still are a practical calculating tool from the ancient world, particularly before the introduction of positional notation. Abacuses are still commonly used today in countries by some merchants and traders, especially in some parts of Eastern Europe, Russia, China and Africa. They are also often used to teach arithmetics to children. Some people who are unable to use a calculator due to visual impairment may also use an abacus. There are several distinctive modern implementations of the abacus, but usually it essentially consists of rows of movable beads corresponding to powers of 10 sliding on wires. These represent digits and can come in various different forms. For a particular design, there are numerous different ways to perform calculations. These operations may include the 4 basic operations and also square and cube roots. Usually one of 2 numbers is set up. The beads are then manipulated to implement an operation involving a second number. Some calculation methods might also work with non-natural numbers such as 1.5 and 3/4.
For the rightmost rod, the value of the beads on the lower deck are 1. On the next rod, the beads on the lower deck are worth 10, and on the next rod 100, and so on. The upper beads are worth 5, 50, 500. That means that every upper bead is worth 5 of the lower beads on the same rod.
Many centuries later, in 1623, the first mechanical calculator was designed by Wilhelm Schickard. His machine was composed of 2 parts, an abacus to simplify multiplications and divisions, and the mechanical part with a dialed pedometer to perform additions and subtractions. However, his machine was unreliable and limited by the technology of its time. Surviving notes of his suggests that the machine would have jammed after a few entries on the same dial. It could also be damaged if a carry had to be propagated over a few digits. Schickard soon abandoned his project and never mentioned it until his death in 1635. This likely happened after one of his prototypes was destroyed in a fire in 1624. 2 decades later, in 1642, French mathematician Blaise Pascal solved some of these particular problems, inventing his mechanical calculator, the Pascaline. Aiding his father as a tax collector, his calculator helped him in the large amount of calculations required for his job. The calculator was especially successful in its design of its carry mechanism, which adds digits 1 to 9 on one dial and carries 1 to the next dial when the first dial changes from 9 to 0. His innovation made each digit independent of the state of the other, enabling multiple carries to rapidly fall from one digit to another regardless of the machine's capacity. After 50 prototypes, he presented the device to the public in 1645. During the next decade, Pascal built 20 more machines, many of which improved his original design. In 1649, Louis XIV of France gave him a royal privilege to design and manufacture calculating machines in France. Although not commercially successful at its time, many if not most later calculator designs were directly inspired by his invention. Expanding on Pascal's ideas, around 1673 German mathematician and philosopher Gottfried Leibniz demonstrated a digital mechanical calculator. This came to be called the step reckoner, and its design was completed in 1694. It was the first calculator that could perform all 4 arithmetic operations, that is, addition, subtraction, multiplication and division. However, just like previous entries on this list, the calculator could not work reliably. This was due to its intricate and precise gearwork. Therefore, only 2 prototypes were built. Despite its flaws, the step reckoner was highly influential to future calculator builders. This was mainly due to its operating mechanism, called the Leibniz wheel or step cylinder, hence the name of the device. The step cylinder was used in many calculating machines for more than 200 years after its invention. In 1702, more than a century before George Boole, Leibniz developed logic in a formal, mathematical sense on the binary numeral system with his writings. In his system, the ones and zeros represent true, false, or on-off states. For this, Leibniz by some is considered to be the first computer scientist and information theorist. He is also one of the first people to propose the idea of artificial intelligence. The considerable progress in the invention of calculating tools in the 17th and 18th centuries can likely be attributed to John Napier's discovery of logarithms for computational purposes in the early 17th century. John Napier was a Scottish landowner and mathematician, best known as the discoverer of logarithms. The computing devices demonstrated so far weren't reliable and efficient enough for commercial use. However, this changed in 1820 when Thomas de Colmar invented his simplified arithmometer, launching the mechanical calculator industry. The arithmometer was the first digital mechanical calculator, strong and reliable enough to be used in a daily office environment. It could add and subtract two numbers and perform long multiplications and divisions effectively by using a movable accumulator for the result. After its debut in 1851, the mechanical calculator industry was launched. The arithmometer, being accurate and reliable, was manufactured from 1851 well into the 1970s, and it was the first commercially successful mechanical calculator. It was also the only mechanical calculator in commercial production from 1851 to 1890. It is important to note that till the late 1800s the word computer referred to a human performing calculations. It is only in the late 1800s that the word was actually used to describe devices. Charles Babbage, the son of a London banker, was an English mathematician, philosopher and mechanical engineer who studied at the University of Cambridge. Babbage by many is considered to be the father of the modern computer. At the height of the Industrial Revolution in 1822, he started designing his hand-cranked mechanical calculator called the difference engine. The difference engine could calculate polynomials up to the 7th degree, relying on the mathematical principle of finite differences. The device was automatic and error-free. The purpose of the difference engine was to standardize the many mathematical tables of the time. It was also to allow calculations to be more accurate, since there were many errors in these mathematical tables. These errors could often lead to accidents, with for example ships and railways. Charles Babbage turned to the British government to fund his project and soon got a contract with a loan. In 1832 he only built a small demonstrative model of his difference engine. While designing the difference engine, he came up with a new idea of a full-scale, programmable, multi-purpose mechanical computer. This came to be called the analytical engine. The analytical engine would have been infinitely programmable with its punch card system. It also would have had an incorporated arithmetic control unit, control flow in the form of conditional branching and loops, and integrated memory, just like the modern computer. Simultaneously, he also came up with a second simplified version of his difference engine called the difference engine number 2. This required less parts and could calculate polynomials up to the 30th order. It also had an inbuilt printer that would automatically print its result. This device too had to be hand cranked and required a turning wheel to be turned at a constant and steady rate. The British government refused to fund his project. As you can tell, Babbage never actually managed to build any of these machines and would quickly move from one project to the other. Parts of Babbage's incomplete mechanisms are on display in the London Science Museum. In 1991, the difference engine number 2 was built from Babbage's original plans and materials authentic to the 19th century materials Babbage would have used. It turns out his second difference engine would have worked. A person working close to Charles Babbage was Ada Lovelace. Ada Lovelace, the daughter of a famous English poet and politician Lord Byron, is considered to be the first person to ever write a computer algorithm, giving her the title of the world's first programmer. She was encouraged at a young age to pursue a career in science instead of art. She soon met Charles Babbage at the University of Cambridge, who at the time was a professor there. Note that many influential scientists and inventors at the time were multidisciplined. so they didn't have the specialization we have today. In 1843, she wrote an algorithm to compute the Bernoulli numbers. She did this while writing a translation of a description of Babbage's analytical engine to an Italian military engineer and appending her own notes. This is considered to be the first published algorithm ever specifically tailored for a computer. In 1890, the US government faced a serious problem regarding its census. The US Constitution requires a census to be conducted every 10 years for the purpose of government planning. Due to a large-scale population increase, mainly due to immigration, the US population had increased drastically from 1880 to 1890. The 1880 census took about 9.5 years to complete. It was predicted that the 1890 census would take 13 years. This is where Herman Hollerith, an American businessman and inventor, comes in. Hollerith designed an electromechanical tabulator machine. The tabulator provided an efficient and organized way to represent information. The machine used a punch card system to represent data. The punch cards would then be inserted into a so-called reader and organizer, and the data would be represented on meters on the device. The census was eventually completed in about 6.5 years, despite a population increase of 16 million. The tabulator saved billions of dollars for the US government, and businesses would soon recognize the importance of computing devices. Hollerith later founded a tabulating machine company that would later merge with other machine-making companies. This led to the formation of the well-known International Business Machines Corporation, or IBM, in 1924.
Creation of the computer. After the 1920s, the expression computing machine referred to any machine that performed the work of a human computer, especially those in accordance with effective methods of the Church-Turing thesis. The thesis states that a mathematical method is effective if it could be set out as a list of instructions able to be followed by a human clerk with paper and pencil, for as long as necessary and without ingenuity or insight. Machines that computed with continuous values became known as the analog kind. They used machinery that represented continuous numeric quantities, like the angle of a shaft rotation or a difference in electrical potential. Digital machinery, in contrast to analog, were able to render a state of a numeric value and store each individual digit. Digital machinery used difference engines or relays before the inventions of faster memory devices. The phrase itself, computing machine, gradually gave way after the late 1940s to just computer, as the onset of electronic and digital machinery became common. These computers were able to perform the calculations that were performed by the previous human clerks. Since the values stored by digital machines were not bound to physical properties like analog devices, a logical computer based on digital equipment was able to do anything that could be described purely mechanical. The theoretical Turing machine created by Alan Turing is a hypothetical device theorized in order to study the properties of such hardware. In 1936, Alan Turing and Alonzo Church independently and also together introduced the formalization of an algorithm with limits on what can be computed and a purely mechanical model for computing. This became the Church-Turing thesis, a hypothesis about the nature of mechanical calculation devices such as electronic computers. The thesis claims that any calculation that is possible can be performed by an algorithm running on a computer, provided that sufficient time and storage space are available. In 1936, Alan Turing also published his seminal work on the Turing machines, an abstract digital computing machine which is now simply referred to as the Universal Turing Machine. This machine invented the principle of the modern computer and was the birthplace of the stored program concept that almost all modern-day computers use. These hypothetical machines were designed to formally determine mathematically what can be computed, taking into account limitations on computing ability. So if a Turing machine can complete the task, it is considered Turing computable. Akira Nakashima invented the switching circuit theory in the 1930s. He published a series of papers showing that the two-valued Boolean algebra, which he discovered independently, can describe the operation of switching circuits. This was due to the fact that he was unaware of George Boole's work until 1938. This concept of utilizing the properties of electrical switches to do logic is the basic concept that underlies all electronic digital computers. Switching circuit theory provided the mathematical foundations and tools for digital system design in almost all areas of modern technology. The world's first electronic digital computer, the Atanasov Berry computer, was built on the Iowa State campus from 1939 through 1942 by John V. Atanasov, a professor of physics and mathematics, and Clifford Berry, an engineering graduate student. So this is the Atanasov Berry computer here. In 1941, Konrad Zuse developed the world's first functional program-controlled computer, the Z3. Zuse also developed the S2 computing machine, considered the first process control computer. This here is the Z3, or the Z3. He founded one of the earliest computer businesses in 1941, producing the Z4, or the Z4, which became the world's first commercial computer. This is the Z4. In 1946, he designed the first high-level programming language, Plankalkül, or whatever. I don't know how to say it. In 1948, the Manchester Baby was completed. It was the world's first electronic digital computer that ran programs stored in its memory, like almost all modern-day computers. The influence of Max Newman's Turing's seminal 1936 paper on the Turing machines and of his logico-mathematical contributions to the project were both crucial to the successful development of the baby. In 1950, Britain's National Physical Laboratory completed the Pilot ACE, a small-scale programmable computer based on Turing's philosophy. With an operating speed of 1 MHz, the Pilot Model ACE was for some time the fastest computer in the world. Turing's design for ACE had much in common with today's RISC architectures and its code for a high-speed memory of roughly the same capacity as an early Macintosh computer, which was enormous by the standards of his day. Had Turing's ACE been built as planned and in full, it would have been in a different league from the other early computers. Claude Shannon went on to found the field of information theory with his 1948 paper titled A Mathematical Theory of Communication. This applied probability theory to the problem of how to best encode the information a sender wants to transmit. This work is one of the theoretical foundations for many areas of study, including data compression and cryptography. From experiments with anti-aircraft systems that interpreted radar images to detect enemy planes, Norbert Wiener coined the term cybernetics from the Greek word for steersman. He published Cybernetics in 1948, which influenced artificial intelligence. So this based the basics of AI. Wiener also compared computation, computing machinery, memory devices, and other cognitive similarities with his analysis of brainwaves. The first actual computer bug was a moth. It was stuck in between the relays of the Harvard Mark II. While the invention of the term bug is often but erroneously attributed to Grace Hopper, a future Rear Admiral in the US Navy, who supposedly logged the bug on September 9th of 1945. Most other accounts conflict at least with these details. According to these accounts, the actual date was September 9th of 1947, when operators filed this incident, along with the insect and the notation, first actual case of bug being found. So, John von Neumann's architecture, or Neumann János's architecture. In 1946, a model for computer architecture was introduced and became known as the von Neumann architecture. Since 1950, the von Neumann model provided uniformity in subsequent computer designs. The von Neumann architecture was considered innovative as it introduced an idea of allowing machine instructions and data to share memory space. The von Neumann model is composed of three major parts: the arithmetic logic unit, the ALU, the memory, and the instruction processing unit, the IPU. In von Neumann's machine's design, the IPU passes addresses to memory, and memory in turn is routed either back to the IPU if an instruction is being fetched, or to the ALU if data is being fetched. Von Neumann's machine design uses an RISC, reduced instruction set computing architecture, which means the instruction set uses a total of 21 instructions to perform all tasks. With von Neumann's architecture, main memory along with the accumulator, which is the register that holds the result of logical operations, are the two memories that are addressed. So the main memory and the accumulator. Operations can be carried out as simple arithmetic conditional branches, like addition, subtraction, multiplication, and division. The conditional branches are more commonly seen nowadays as if or while statements. The branches serve as go-to statements. The logical moves between the different components of the machine, that is, a move from the accumulator to memory or vice versa. Von Neumann architecture accepts fractions and instructions as data types. Finally, as the von Neumann architecture is a simple one, its register management is also simple. The architecture uses a set of 7 registers to manipulate and interpret fetched data and instructions. These registers include the IR, the instruction register, the IBR, the instructions buffer register, the MQ, multiplier quotient register, the MAR, memory address register, and MDR, memory data register. The architecture also uses a program counter, or PC, to keep track of where in the program the machine is.
The making of the transistor was a huge step forward in computer science and technology, because the previous electronic switches, vacuum tubes, are big in size and also waste a lot of energy because they need to heat up the filament. The first transistor was made in 1947 on December 24th by Walter Brattain. This was made using two plates of gold and germanium pressed together. The making of the transistor began the second generation computer, and up until the 1960s these used separate transistors on circuit boards with magnetic core memory. These were in mainstream use in the 1950s and 60s. While vacuum tubes usually took up several cubic centimeters, the first transistors could be as small as half a cubic centimeter or even smaller. The first commercial fully transistorized calculator was made in April 1955 by IBM, and it was called the IBM 608 transistor calculator, which was shipped in December 1957. Transistors also had a huge advantage compared to vacuum tubes, which is reliability. And while vacuum tubes, because of the high working temperature and filament, were quite unreliable, transistors were quite the opposite. They could function for multiple years or tens of years without failing. These transistors also had a much shorter switching time compared to vacuum tubes, which is 0.3 microseconds. These computers used magnetic core memory as their main memory, which is a huge step forward in memory technology compared to their previous version, which most computers used Mercury delay line memory. Magnetic core memory has a few key advantages compared to Mercury delay line. The first and biggest is mainly that it can be accessed in a random order. The second is, of course, size, because even the first magnetic core memories were a lot smaller than Mercury delay line systems. These could go up to around, these had a density of about 32 kilobits per cubic foot in the late 1960s, but it wasn't much smaller in the beginning. The basic concept of using magnetic materials for storage is as old as computing is itself, but the first actual usage was the MIT's Project Whirlwind computer, which required fast and random access memory for a real-time aircraft tracking system, and of course Mercury delay lines couldn't make this possible. The first commercial application was done by the Sieber company in the early 1950s with its new range of jukeboxes, starting with the V200, developed in 1953 and released in 1955. Numerous uses in computing, telephony, and industrial control followed after this, and this is where magnetic core memory really took off. The second generation also brought with itself a lot of important innovations in computer architecture, such as index registers for controlling loops and floating point units for calculations based on real numbers. Prior to this, accessing successive elements in an array was quite tedious and often involved writing self-modifying code, which are programs that modified themselves as they ran, which is obviously really frowned upon these days because you cannot really debug them efficiently, and is also quite literally impossible in most high-level programming languages. In the second generation, also floating point calculations were done in hardware, compared to the first generation, in which they were done by libraries. This is also the time where many high-level programming languages were introduced, including Fortran in 1956, Algol in 1958, and COBOL in 1959. Important commercial machines of this era include the IBM 704 and its successors, the 709 and 7094. The second generation is also the first computer generation that saw supercomputers, which are computers that are an order of magnitude more powerful than other machines of its time. These two are the Livermore Atomic Research Computer, or LARC, and the IBM 7030, aka Stretch. And these machines also had a primitive form of parallel computing, which was never heard of before. The third generation of computing, from 1963 to 1972, brought huge gains in computational power. This is a time where ICs, or integrated circuits, which mean multiple semiconductor devices on one single component, were introduced. Usually around 10 or so devices per circuit or chip was the first, which is called small-scale integration, or SSI for short, and it evolved to the end of the third generation into MSI, or medium-scale integrated circuits, which had up to 100 devices per chip. Multi-layer printed circuits were developed, and core memory was replaced by faster solid-state memories. Computer designers began to take advantage of parallelism by using multiple functional units, overlapping CPU and I operations, and pipelining in both the instruction stream and the data stream. In 1964, Seymour Cray developed the CDC 6600, which was the first architecture to use functional parallelism by using 10 separate functional units that could operate simultaneously and 32 independent memory banks. The CDC 6600 was able to attain a computational rate of 1 million floating point operations per second, or 1 megaflop. 5 years later, also developed by Seymour Cray, was the CDC 7600, which was able to attain around 10 megaflops. The fourth generation of computers, from 1972 to 1984, is the first time large-scale integration, or LSI, meaning 1000 devices per chip, and very large-scale integration, or VLSI, meaning up to 100,000 devices per chip, were introduced. At this scale, entire processors will fit into a single chip, and entire systems meaning processor, main memory, and I/O controllers, can fit into a single chip for simpler computers. Gate delays were also reduced to about 1 nanosecond per gate, which means a lot faster computing. Semiconductor memory also replaced the main memory in most systems, from core memory to semiconductor memory. Developments in software include a few very high level languages, just FP or functional programming, and Prolog, such as meaning programming in logic. These languages tend to use a declarative programming style as opposed to the imperative style of Pascal, C, Fortran, etc. These languages are not yet commonly used, but show huge potential in programs that we run on massively parallel computer systems, such as systems with over 1,000 processors, separate processors. Two very important events also in this generation include the development of the C programming language and the Unix operating system, both at Bell Labs. The main improvement, the fifth generation of computers from 1984 to 1990 brought with itself, is the widespread use of parallel computing. Up until this time, parallelism was limited to pipelining and vector processing, or at most a few processor sharing jobs. The fifth generation saw the introduction of machines with hundreds or thousands of processors that could all be working on different parts of a single problem. The scale of integration in semiconductors continued at an incredible pace. By 1990, it was possible to build chips with 1 million components, and semiconductor memories became standard on all computers. Other new developments were the widespread use of computer networks and the increasing use of single-user workstations. Up until this time, it was very rare to see people with workstations of their own. Usually they shared hours on a bigger computer. Prior to 1985, large-scale processing was viewed as a research goal, but two systems introduced around this time are the typical first commercial products to be based on parallel processing. The Sequent Balance 8000 connected up to 20 processors to a single shared memory module, and the DEC VAX780 as a general-purpose Unix system with each processor working on different users' jobs. Scientific computing in this period was still dominated by vector processing. Most manufacturers of vector processors introduced parallel models, but there were very few 2 to 8 processors in these parallel machines. In this era of computer networking, both wide area network, WAN for short, and local area network, LAN for short, technology developed at a rapid pace, stimulating a transition from the traditional mainframe computing environment toward the distributed computing environment in which each user has their own workstation for relatively simple tasks, for example, reading emails or compiling programs, but sharing large or expensive resources such as file servers and supercomputers. This way of computing still dominates today's world. This is a picture of the DEC VAX780. The sixth generation of computers are where we are today now. It's from 1990 to today, and this generation has brought with itself a lot of new improvements. This is where the biggest improvements come in the shortest amount of time, meaning the rate of new research really increased. This is also the era where Moore's law was introduced by Gordon E. Moore, who was one of Intel's founders. This law states that around every 18 months, the computational power of integrated circuits doubles. This held true up about until 2017 to 18, and since then has been dropping off steadily. The sixth generation introduced a really big focus on short-range communication, AI development. Today's largest supercomputer is the Fugaku supercomputer, powered by an A64FX ARM-based processor developed by Fujitsu. And this has a peak computational capacity of around 513.855 petaflops. This is a picture of the said computer. Informatics is the study of natural and engineered computational systems. In 1972, the first email software was born. In 1974, the word internet was coined in a TCP protocol study. In 1983, the previously really secured ARPANET turned into MILNET, or military network, which is the military segment of the internet. In 1988, the first big virus, which was a worm, really took off. By the end of the 1980s, the more and more countries made spy networks based on the NSF net.